Thank you. Thanks to the organizer to give this talk. So, looking, when I first looked at the title of this trimester, I thought, well, maybe a little bit tangential what I was trying to tell you. But Sergey said, well, this is maybe some interest for some applications. Well, let's see. So it's about lattice point counting, a very classical problem in mathematics, and this multivariate central limit theorem for certain sets. So what we will do is, first of all, review some of the very classical problems the last century in lattice point counting related to the distribution of values of quadratic forms, because we are interested in the number of lattice points in certain parts of hyperbolas and, of course, ellipsoids. And then there's some application which is traditional hard problem in number theory, that is estimating what is the smallest value for indefinite forms not being zero. And then I will sketch some of the proof ideas, that is some inequalities for so-called multivariate zeta functions, and some phenomenon which is used not only in number theory, but also in classical works in probability theory, and that is the so-called gap properties for Fourier inversions. And finally, I would like to sketch what is the link between something probabilistic, the multivariate center limit theorem, and the analytic number theory results. And it turns out that one is, so to speak, based on the other. Now, to just focus on this, the problem, we take a d-dimensional lattice, standard lattice, and we count the number of lattice points called volume of Z in this ball with radius square root of S. So this is easy enough, and what we want to compare it with is, of course, the volume of that ball, the same ball. Now, when we hit a lattice point on the boundary of the ball, that is of radius square root of S, then the counting goes up by 1. So what we do, we count the number of lattice points on a squared radius of an integer, which is an integer n. And if we want to compare now the first obvious estimate, the number of lattice points with the volume, then it's obvious that if we take the squared radius over a certain interval I, then there are one function's jumps, that is a counting function, whenever lattice points are on the boundary of the ball, whereas the volume function just is differentiably smooth increasing. So there is a gap between both at these points, and it is of the size of the number of lattice points on radii, which is a square root of integers. And that is unavoidable in the comparison of something smooth and something jumpy. And in order to find now a lower bound, you have to know something about this number of lattice points on the boundary of a ball. And that is a very simple observation. This is the pigeonhole principle. You take a big cube of lattice points in Rd, between minus R and R, and look at the value of this Euclidean norm squared on this big cube. So it ranges from 0 to dr squared on the cube. And now you apply the pigeonhole principle. So if you do this mapping, and it goes from 0 to dr squared, and you have 2r plus 1 to the power d lattice points in the cube, then one of those values in the range got to catch r to the d minus 2, namely this quotient of values. So there is a lower bound in the discrepancy between volume and that of this order, at least, at some r. That is unavoidable by the whole thing. Okay, now the question is, what is the actual behavior depending on dimension? And this is a very old question. So let's start with dimension 5 or larger. And here we have two gentlemen named Hardy and Mordell, who've already proved in 1918 and 1920 upper and lower bounds for the number of lattice points on the boundary of a ball with integer, with radius squared being an integer. And it's in this integer given by this two numbers, which means this r to the, where here square root of n is r, so it's the upper and lower bound which I were giving before. So it's something regular starting at dimension 5 to have this number of points on the boundary, and that limits the comparison in bolts. And that is, so to speak, a regular domain starting at dimension 5. Now going a little bit deeper in dimension, we come to Lagrange, Jacobi, and Walvis. And Lagrange said every number is a sum of 4 squares of integers. Fine. Jacobi gave a formula for that, namely the number of representations of an integer as a sum of 4 squares is just the sum of the 8 times the sum of the divisors, which are incongruent to 0 mod 4. And Walvis just added a little observation that if we take a number which has many factors, like let's say k factorial, then this number is n log n. So the heuristics for 5 and larger would predict in 4 would predict n. But here it's more. And if you take n to be a prime number, then there are at least 8 or so, maximum of 4 representations. So it goes from, let's say, 8 to n log n, and it's a big variety. But any number has a representation of this. And it's even worse, and I don't go that for dimension 3 and dimension 2, which are also well-known classical problems. So dimension 5 and larger is, so to speak, the regular domain for these comparisons. Okay, now we generalize the problem. We now take not a sum of squares, but a general quadratic form with a coefficient matrix Qij, which is positive. So it's a positive definite form. And in this case, we start with the value 0, then comes the minimal value over all the integer vectors, and so on. And we can order them according to size for positive forms. And we will assume that Q is irrational. And Q irrational means it's not a multiple of a real multiple of a rational matrix. So not a real multiple of a rational matrix.
This photo is for whom?
Pardon?
This photo.
This is Davenport. That's Davenport. And so Davenport and Lewis in 1972, they made the following conjecture for all irrational forms, as not multiple of rational forms, and dimension at least 5, the values ordered turned out to be dense at infinity. So the consecutive distance certainly goes to 0, and then goes to infinity. And for the diagonal case, this was long done by students of Landau, Walvis, and Jarnik in something like 27, 28. But the question was what happens for general matrices. Okay. Now, this is a consequence of the following results, and this is lattice point counting. So this, you would call distribution of values. But if you have a rather accurate lattice point counting, you can deduce this thing. And what you do is you take an ellipsoid with squared radius s plus delta and squared radius s, and the shell between. And you count the number of lattice points within this thin shell, which is very thin. It's of order 1 over r, 1 over square root of s. And you compare those number of those lattice points with the volume of this shell, and subtract 1. And then you can see that this is going to 0 as the squared radius goes to infinity. And out of this is very easy. You can see that this property will follow. So this is something I was able to prove after a long while for dimension 5, and larger. Okay, now this has now got an extension, this result, namely with a result which generalizes the regions, not only ellipsoids, but certain types of truncated hyperbolas. And this is joint work with Grisha Margulis and 2 graduate students of ours. And it says the following: yes, we have the same result, but we can now make the counting rather explicit or effective in the following way. So we have eigenvalues of the matrix between a lower bound Q0 and an upper bound Q. We take, first of all, the positive definite forms and correspondingly the ellipsoids. And you try to evaluate now the error in the ellipsoid, in the volume, in the lattice point counting for the ellipsoid. And there you see, well, the familiar r to the d minus 2, that is codimension 2 to the volume. Then there comes a number theoretic function. And then there comes something which is a much smaller term, which is, compared to the first term, reduced by a factor r to the d minus 2 plus 2, which is really going to 0 for d greater or equal to 5. And here, this number theoretic function turns to 0 if radius goes to infinity, if q is irrational, for any irrational matrix. And you can work out what this is in terms of Diophantine properties of the matrix and really quantify it to some extent, how fast it goes to 0. Okay. So the proof this is based on results for, as I said, positive as well as indefinite form. It's one theorem for all, and it includes the previous one. So now older results for the indefinite case were obtained by Margulis and his school, Esken and Moses, already in 1998. So when you take now the hyperboloid, that is, Q is indefinite, so this shell is, so to speak, a hyperboloid shell, and that has an infinite number of lattice points, so you need to count all the lattice points in a certain window omega, which you scale up by a factor of r, big window. And then you get a prefactor, depending on the width of the shell, and again the r to the d2 minus 2. And this works not only in dimension 5, but already in dimension 3 for signatures 2, 1, and 3. That's the only one for indefinite form. And 2, 2 are in dimension 4. So, now, how does it look like? So, we have irrational form. We have signature of the indefinite form, which is, and what we do is now depicted in geometrically. We now count lattice points in these hyperbolic shells. There would be, as I said, infinity of them if we don't take a big box for counting things in this shell. And what this theorem says, okay, it goes the relative number of lattice points in the shell divided by the volume of this restricted shell goes to 1. as r goes to infinity. What we tried to do in the recent paper was to not only, this result only works for very thin shells. And what we wanted to do is we take big shells, wide shells, so a real hyperbolic region, and try to make this lattice point counting work. Now there is a certain problem with that. But first of all, this was for Margulis, I guess, in 1986, a great event, because he could prove this already for dimension 3 for indefinite forms. And that was, I guess, why he got the Fields Medal at that time. Because that was out of the reach of classical analytic number theory, with the usual Fourier analytic methods. So this is Mr. Oppenheim up there, who made this conjecture, the famous conjecture in 1929. So this one here, what we proved is dimension with effective bounds is up starting in dimension 5, but he could prove it ineffectively already that the set of values of an indefinite irrational form is dense in R. Here you have not dense at infinity as for positive forms, but dense everywhere. Okay. Now, what are the results now? This doesn't seem to... So, you see, I spelled it out. We have a hyperbolic region. We have a box. But now, if we slash more than a thin shell out of this box, we will have a problem. Namely, that there are not only points maybe on the boundary of the hyperbolic region, but there may be also lattice points on the box boundary. And if the box boundary is aligned with the lattice, I'm likely to catch a lot of lattice points if I'm not careful. So I have to rotate the box or the lattice, whatever, in a certain nice irrational way to get something which is called an admissible lattice, which means that the product of coordinates of any lattice points which is not 0 is bounded below. And you can construct such lattices explicitly very easily. So this is forbidding, don't try to read it. It is now that's something like in the positive definite case, there is two types of functions at least, which when the parameters are, over which I take infimum, are going to infinity, it goes to 0 for Q irrational. But it is much more involved. It's understandable because there are now two types of region involved, the box and the, but this works for wide shells. That is, here A and B are not very close to each other, the values of the indefinite form, but they could be quite large and different. So, and this one, of course, can get back all the things we have been talking about for dimension 5 and larger we had before. So this goes to 0, and all these two quantities which are here on the second line also go to 0 if we have irrational. And we could make properties of the matrix Q. If they are Diophantine, then we can specify a better rate here. Good. Now, what is the application? Why is one interested in number theory in this? The classical question is, we have an indefinite form with signature R and S, and is there a solution of the inequality absolute value of the indefinite form smaller than 1? And if there exists a solution, that is not meant the trivial solution 0, but what is the size of the smallest solution to this inequality in quadratic forms? And here you see there is in this maximum eigenvalue of the form, there is some complicated exponent and some quantity rho, and this rho depends on the signature. So that, in order to make it more simply understandable, if we have the coefficients of the matrix bounded by C, and we are asking for a solution to a quadratic form smaller than some arbitrary small epsilon, how large we would have to take in size the first solution to this inequality. And you see here is some bounds. It's epsilon to the minus 1/5 over d. So there are certain cases if d is larger or equal to 12 and r is equal to s plus 3 for the signature, then I have this bound. Otherwise, for the small dimensions, I have here a certain number of bounds. This is also special in the sense, these two restrictions, when the isotropic dimension of the quadratic form is d0. Is small. Now for random forms, things are much easier. So I get a very small solution for random forms if of the size epsilon to the minus 2d over d minus 2. For d greater or equal to 3, almost surely. This is due to a Theorem some years ago. So this rho, where does it come from? This doesn't work this way. Take it this way. There is one philosophy. If you try to solve these questions for forms with real coefficients, first try the classical ones, quadratic forms with integer coefficients. They have actually zeros, starting at dimension 5 for indefinite forms. This is a very old result by Meyer, 1884. There exists always one. And then people have bounded, this says were Kessels and Birch Davenport, the smallest solution to this exact equation for general A, and Schlickewein in 1805 was then coming up with maybe the best bound, and the best bound really depends on the signature of this integer quadratic form. You see there are various cases, and d0 is the dimension of the maximal isotropic subspace. So to take home, if we have, so to speak, a balanced form with positive and negative eigenvalues number equal, then it's in the limit, so to speak, 1/2 this row here. And why is this interesting? Because you think, yeah, now I take a form with integer coefficients, I deform the integer coefficients a little bit to be irrational, and then I hope to get maybe a related bound in the results. That is just a hope, but it is usually very difficult to prove. So, and in the diagonal case, things are much easier. So the row appears here too, and we have a very nice exponent. Okay, so what are the tools? Now this is a Fourier theory. And let me start with the a little bit more involved case where we take the intersection of two areas. That is, one is a hyperboloid with its infinite, and then we intersect with a box or window. And here we do the following. We rewrite the indicator function of this box by means of an infinitely differentiable function kappa and some weight which is near the origin. It's nearly 1, and later on it's more. The reason for doing it is we do a twofold Fourier inversion, one for the ellipsoid values between A and B, so this is a one-dimensional Fourier inversion, and for the box we do a d-dimensional Fourier inversion. And this value here comes in to the, so to speak, Fourier transforms here. There is one, which is the so-called Siegel zeta function. This is an exponential.
No colors.
So it's an exponential of a complex quadratic form with positive real part. This is the Q plus, is the real part of Q, the positive part of Q, and there's some linear term here. And it is compared with the same expression, but not in the sum, but in the integral. So, and what you do is you have to integrate this thing over these two variables, the shift v and the frequency t. So the thing to do here is now to square it and try to estimate the absolute value by squaring. And what comes out is it's an estimate by another type of zeta function, but one which is really nice, because here this omega is a positive form and it's double dimension. Double dimension because we squared these sums here. And so it looks like this. It looks like this. There is m and m bar, both d-dimensional, and I have a positive form here in m and m bar. And so, I don't know when we have time to, so already spent half an hour. So this one here is a simple argument which is used sometimes in analytic number theory. It's in the original form, it's going back to Weil, but here it's a modification. And it's just something like you have summation over a Cartesian product of lattices. And what you do in the Cartesian product, you take the sum and the differences of two vectors from the two summations. That is, you rotate the thing by 45 degrees. Unfortunately, this makes the sum and difference not really independent, but they are depending mod 2. So, conditioned on the parities, but you can treat them as independent, and once you treat them as independent, you use Poisson summation in one of the variables, here the sum of both vectors, and get some nice exact formula, and then estimate in the other variable taking absolute values and arrive at this type of thing. Okay, now we are at this positive quadratic form, which is the squared Euclidean norm of elements of a transformed 2D-dimensional lattice, which depends on two parameters, t and r. So we lost the shift in the way, and we won't by taking absolute values. And that is something. This is an unimodular lattice, and it has some nice duality properties. So what we get here is a sum over all elements of this lattice depending on these two parameters of x to the minus e squared. And that is quite easy to see what this is. It is the density of this lattice in a box of size 1 divided by the volume of that lattice, bounded by that. And now comes geometry of numbers. Because how do you estimate the number of lattice points of an arbitrary lattice in a box? So you look for some kind of nearly independent generators of your lattice called Minkowski minimas, and look how many times does a multiple of each generator still fit into the box. And these are the so-called Minkowski minimas, and their reciprocal is this here, and there's the smallest one which you can use to upper bound it, and the whole thing is larger, smaller than r to the d. So these are the Minkowski first d successive minima, and since we have some nice duality in this lattice, there is a duality between the j's and 2d, d plus 1 minus j Minkowski minimum. So M1, we come back to that, is just the smallest, the length of the smallest non-zero vector in this length. And what you have to do now is quite clear. You take this bound here and you integrate it over t. Now at any time, for any t, that lattice changes. And the question is, how does this quantity, let's say the first successive minimum in length, how does it change with t? And this is a problem to be solved for general Q, and we did that back in the 90s, and I could do it extended to dimension 5 and positive forms. So the question is, just to put it like this, you have here the Poisson summation thing, and here you have another thing which is more or less r to the d minus 2, with some codimension. And to prove this codimension 2, that is the problem, what you have to do. And in the general case, for indefinite forms, one had to use representation theory of SL2R, one had to use averages over unit potence subgroups, which Margulis developed with his group. And I used just in the positive forms, I just used the performance of the first successive minimum. Okay, now I said this is all something has to do with gaps in Fourier transforms. What do I mean by this? We take this theta function at the point frequency t plus epsilon multiplied by a conjugate of t minus epsilon. And then we make this rotation, transformation of the two-dimensional sums, and get this expression, which has a positive part, positive definite part. It has a shift part in the two things, so it's bilinear, and it has a quadratic part, but now with an epsilon frequency. So the sum over all the L variables here equals this quantity. It's a theta function for this shift and at the point epsilon, and then one part of this here and one part of that. And if I estimate this by the supremum of this theta function times r to the d, then I get out something like first successive minimum at the frequency epsilon times r to the 3d. Now the point is, I'm taking the product of the theta function for any very large t, just at these two adjacent frequencies, and get out a bound which is in terms of this Minkowski minimum for a very small frequency. And this behavior from zero, frequency 0, down for the neighborhood of 0, that you can estimate. That is something you can do. And I will show you how in a picture. And it is done in the following way. First of all, you estimate the first successive minimum. It is the minimal value of this thing here. So there are two cases. M bar is 0. Then you take a non-zero vector. This gives you a 1, minimum 1 here. And if M is 0, M bar is 0, then you get here an epsilon. So you get R epsilon plus thus of this case. Or the M bar is non-zero, then M and M bar are related by 1 over epsilon. And you put that into this, and then you have this other bound. So this is a simple argument, twofold argument. And you get this one here. You get a certain function in epsilon and r, which is smallest if epsilon is very near to 0, 1 over r. And it looks like this. Look at this curve. This is the boundary here. So if both rescaled values of your Fourier transform are large, then what happens? That means that epsilon could be small or epsilon could be large. That is the product here, bound for the product. So between that epsilon small and epsilon large, there is gap. And look at a typical function here in the neighborhood of 0. You see here there is, before things start to pile up again in the absolute value, there is a gap. This is this gap here. And it is also between other values, where you have to compare things which are very high peaks with very high peaks and not frequencies which are not very near to us. You have to have this gap. Using this gap by Lebesgue integration, you can say, well, this function integrates, and because also this speed of decay here is r squared. So the intervals where the peaks are of order 1 over r squared, then there's a big gap, and so you get the 1 over r squared. So it's a simple analytic way of doing things here. Okay, now finally, what is the relation to probability theory here? So a classical theorem would say the multivariate center limit theorems for balls and ellipsoids, or in this case hyperbolic regions, reads like that. I have random vectors x1 up to xn, IID, normed to be 0 and force moment bounded. And then I look at regions defined by Q of S smaller or equal to R, once under the standard under this Gaussian with covariance sigma, and once for the distribution of these vector sums with these data. And the question is, what is the upper bound here? And the upper bound was known for, in the 90s, for dimensions 8 and 9 and larger, but here the remaining thing we could do between dimensions 5 and 8. And the reasons that this was so similar to the previous one was that it is based on number theory. So if we recall classical bounds on this question here, we're going way back to Essay 1945 with the rate d over d plus 1. And for small dimensions, you can see that the ineffectiveness of our bounds for counting lattice points in balls in low dimension, let's say dimension 2, dimension 3, that transfers to the rates in the central limit theorem. So there's a one-to-one correspondence.
Omega means low bound.
Omega means lower bound, yeah. So we have lower bounds here.
But for dimension 3, is it a correct conjecture or not?
This is, I mean, the upper bound is I picked it as Essay, yeah? And the lower bound is by number theory. We will come to that because we relate now the distributions of these vector sums to lattices. Yeah? And for these special cases of random vectors in lattices, we have then using the lower bounds known from number theory, these things here. Okay. What is that? It is mixture of lattices, what we are doing. Again, we take the same problem. We take here the difference between the distribution of a sum and the distribution of a corresponding Gaussian variable. We integrated, represented by a difference of Fourier transforms, just as with the theta functions we had before. And now we do a trick, which is very stupid in some sense, at first it looks. We use the IIDSC, independence and identical distribution symmetry. Because if we play the following game, if we take random vectors xj and xj bar, and independent coins, 0 and 1, which are independent of those, and then form this mixture. Either we take x1 or we take x1 bar with probability 1/2. And so on. Then we get a new sum involving two sets of random vectors and an independent set of coins. This has obviously the same distribution as the original one. Yeah? So now, but that is due to the independence and identical distribution. So we reverse now the expectations by saying, first let us take the average over the coins and fix the both sets of random vectors. And what we get then is somehow scalar product in this quadratic form of vectors xj and x bar k with multiplied with the coin values alpha. So it's a quadratic form in the alphas with more general new matrices of scalar products. Okay, the result which makes this work is the following, which I will explain. This bound here says this is a probability theory version of the characteristic function. And here's the upper bound by number theory. There's some bound coming from choosing the x and x bars. And here comes a quadratic form A with two random vectors, m and m bar, and a matrix, real matrix, which is near the identity, which I take with the supremum of the neighborhood of an identity, where m and m bar are independent and have an approximate and have a discrete Gaussian distribution on the lattice. And m bar, of course, as a function of m and m bar, is an indefinite form on Z2D. So, this is the result I would like to explain a little bit, because this is a transfer, and now you can imagine, yeah, okay, if you have the object on the right-hand side, you apply all the number theoretic things to this real quadratic, indefinite quadratic form. Yeah. But how do we get there? So what we do is we split n into 6 parts. We condition on the vectors x and x bar, and then we rewrite the thing as sum of 3 parts, and then the original sum, x1 up to xn, which gives you these expressions with 1 minus coins for the difference of x bar and xj. 3 independent parts. And, okay, so if I just average over the coins, I can remove by this symmetrization procedure the Sn. This is fixed anyhow under my expectation. It's just a shift. I can remove it, and I have the sum of 3 norm squared. Now I do something which is called symmetrization, replacing this quadratic form in an exponent by a bilinear form. And the bilinear form has sums of xj minus x bar j with variables which are differences of the coins, which have values -1, 0, and 1. So we are now back to again something like a discrete sum in some space, and now we have to evaluate that. Okay, this is easy enough. If we fix, let's say, one sum and sum over the others, well, it's just a product of cosines, because we get plus minus 0 and plus minus 1. So we have to evaluate over the epsilons who are in here the product of cosines of this. Now, now comes the random choice. We would like to have picked xj and x bar j so that the difference is not near 0. It's different from 0, and the things we pick should also form a nice, span a nice space. Should be really d-dimensional, beyond dimension d, a d-dimensional space. So we have lots of choices for that. To do this, that is larger than kappa, and more sophisticated, we want to have them also spanning a d-dimensional space. And this is with a small arrow, we can do that. And if we have now these things, the subproduct here, then we turn this back with taking, let's say, let's say 1j here, and multiplying it with various epsilon. Now, with the epsilons summed, we have a sum of Rademachers here, which is then a lattice in one coordinate, so to speak, a lattice distribution. The sum of the Rademachers. And then we can do that for conditionally on the other one as well, and we get here sums of such Rademacher things, and in the end, we come to a matrix of scalar products of these differences and multiplied by sums of Rademachers, so some integer coordinates. So in that way, we are, by this very cheap trick of symmetry, we have put in some discrete nature into something which might be very smooth if the distribution of the axes are smooth. But it is a fact that the worst rate of convergence you can get in the multivariate central limitum is that for random vectors from a lattice. Yeah? And in such a way, we just take an average over all these lattices to estimate the classical central limit theorem. So, and the remaining step is now to get the Bernoulli the binomial distributions in each variable approximated by some Gaussian, by local limit theorems, by some Gaussian distribution, and then we are really at the theta functions we wanted to have. Okay, thank you for your attention.